Okay. I actually don't remember the title, but Eliashberg is going to talk about viewability.
So I kind of foolishly thought that I can use the Blackboard for my talk, so therefore I will be writing this from this page I will be given. So this will be a kind of talk, kind of different type that what you have. This conference that can much more, much less algebraic and much more flexible mathematics. And also it's a difference in the sense that there is some theory which I want to say, but I really don't understand what the theory means, because it's like they produce some result which kind of like I don't know how it should be interpreted. Okay, so we start. So we'll be talking about symplectic manifold, and symplectic manifold which we're talking about will be even worse, will be exact, so they cannot be compact, and so this will be say symplectic manifold, which be such that symplectic form is exact. So, for instance, this is a say affine algebraic manifold or Stein many complex manifold, but maybe a little bit more general. And I would like to say, suppose I fix this lambda, which is uniform called, and this Liouville form is a dual vector field, which called Liouville vector field. So I can contract omega, like take a dual to lambda vector field, and this vector field is characterized by properties that equivalent to the Lie derivative of omega along the z is equal omega, which means that like if you consider like flow of this vector field, then it's just scale form. So it's a conformally symplectic expansion of my manifold. So I also will be talking about contact manifolds. And contact manifolds for me they naturally arise in this context, because if you have this vector field z, which one, and then I consider just locally consider space of trajectories. So I consider, for instance, any transverse line, then contact structure is what is invariantly induced on the space of leaves of Liouville flow. So this Liouville flow is what is called foliation. Foliation, so away from it, zero of course, but it's a foliation with transverse contact structure. On transverse leaf, this, if you consider this lambda equal to zero, consider this plane field given by this Papian equation, then it's invariant with respect to flow, and this is our contact structure. So conversely, contact manifold is just kind of can be thought exactly in the same way. So you take a contact manifold, so it's a manifold with non-integrable plane field. Say this is a even odd dimensional manifold, and it always has a symplectization. So you just multiply this manifold by R plus, and consider this. So if you have a, say, for instance, like fixed contact form alpha, then we have this Liouville form S alpha, and you have a vector field Z just scaling along this vector field, and give me precisely kind of locally exactly this picture. So if you like really simplexically minded person and don't like any kind of contact geometry, then you can just think that everything in contact world is just symplectic object in the symplectization, which invariant or equivariant with respect to this action of this flow. So in particular, you can look at this Lagrangian manifold, which invariant, so which look like these cones, and therefore it's kind of the same as looking in the contact case, they project to slice as a n-1 dimensional manifold, and they are called Legendre, and they are maximal integrals of manifold of this non-integrable plane field. So this point of view also kind of suggests looking at hypersurfaces. So suppose you have a symplectic manifold again, and now I do not fix this. It's exact, but I do not fix primitive, and I'm looking at some hypersurface sigma inside X, and I'm asking, is this, if I can find Liouville vector field which is transverse to it. So such hypersurfaces, like we call Gromov symplectically convex, it's also called hypersurfaces of contact type, and you just would like to understand, given hypersurfaces of contact type of node, so you can kind of analyze this thing. So this kind of suggests the following notion. You can consider this domain, symplectic, for instance, compact domain, with boundary, which is a contact manifold. So it kind of leads to this concept of symplectic filling of contact manifold, so symplectic manifold with contact boundary in this sense. And you can also ask if this contact manifold is symplectically fillable, and if it's fillable, then so how many fillings, and what can we say about fillings, and in which extent filling is determined by the boundary. And kind of development of the subject, it was a pretty useful notion. It was a lot explored, and so, for instance, like from the very beginning, we knew many kind of. So okay. So to fix again notion. So what I will be talking about is sometimes they call Liouville manifold with like cylindrical end. So you have a Liouville manifold is non-compact, so you have a complete Liouville flow, and there exists some hypersurface such that this hypersurface, away from this hypersurface, my flow is just product with trajectories. So such manifolds have a kind of canonical contact structure in things. Like there is no kind of fixed contact form. You get contact form if you have particular kind of transverse lines, but it will be kind of irrelevant from what I'm discussing. You have some kind of asymptotic canonical contact structure. So question, how many filling given contact structure has? And so there is a Gromov theorem which says that, for instance, if you take a S3 with standard contact structure, then this Liouville filling unique. It's just standard ball, nothing else. So if you go to high dimension, then you can prove also similar result. If you take a standard contact structure in the sphere, then you have this Liouville filling. Then again, this filling unique up to as a smooth map. There's only, I know that it's R2N, but it's still kind of open problem where there's kind of maybe symplectically it could be non-standard high dimension. This is a kind of at the moment just a little question.
Yes. What are you asking the filling to be you?
What?
You asking the filling to be you?
Yeah, I'm asking. I'm not talking about blocks.
Yes, that's
Right. Yeah. So if this is essentially if you're not asking it like just symplectic filling, then you can do such things like blow up the field, but not much more. So now there is also kind of the following thing you can further ask. So you have this contact menu. So okay. So then this how subject was developed. So well, it was found we know from the very beginning, of course, there are examples. We have a contact manifold, we have a many fields. For instance, you have a link of singularity, isolated singularity, and so this is a contact manifold with kind of singular symplectic feeling. But then if the singularity can be smooth, can be deformed, then it give me precise feeling of this type. But sometimes the space of smoothing is reducible and we have a different smoothing, and therefore we can get different feelings. So such examples were known from the very beginning. But then people went for work hard construct example, we have an infinitely many feelings. So there is a kind of the whole kind of developed industry of constructing feeling and studying what are constraints coming from the boundary, etc. So there is another question about these feelings, which like open problem, and a lot of kind of people try to do something. Is the following: that okay, so you take it as contact manifold, and it has a Liouville feeling. So that means you have some lambda, but now you would like to actually not all Liouville feeling born kind of equal. And so you would like to somehow have better feeling. And there is this condition which you can call this Gromov Weinstein condition. It's a imitate notion of Stein manifold in contour geometry, and it means that this we want that this vector field Z, which we construct, would be Lyapunov. Would be gradient-like field for some function. So there's some function for which the Z is a gradient-like. And this function, then you may not even ask what the behavior of this function at infinity. If you know the Z gradient-like for some function, you can always arrange that this function at infinity have this one of this boundary as its level. So that means that you can so you have this picture that this function may have some critical point, and you just try to but all levels because it's a gradient like that away from singularity, it's again contact manifold, and then what you get, well, assuming say it's function Morse or some kind of reasonable, then you get this picture that your contact manifold you obtain by sequence of circuit surgery, and the surgeries are very kind of easily, precisely can be described. So such feeling is called Weinstein feeling. The Weinstein feeling, that means it's a Liouville feeling, which such that Liouville vector field admit this Lyapunov function, gradient-like for some function. So not every Liouville feeling is Weinstein because of pure kind of topology. Yeah, the level surface because they transverse to the vector field because the gradient like that means that it's
not just gradient like infinity, it's gradient like
yes, the gradient like at infinity kind of doesn't make sense condition. The gradient like means that well, in particular away from critical point, it's a derivative of vector field is positive. So now there is a again example, first example was constructed by Duda Magda that actually so what do we immediately know about Weinstein field? Weinstein field has this as a critical point, and critical point of such function must be of index no more than half. Because what automatically follows that stable manifold of all critical points are isotropic. And therefore you get no more than half index of this critical point, and hence this manifold has a homotopy type of half-dimensional skeleton, half-dimensional code. And what was from early on was an example of Duda Magna, which kind of constructed example when feeling not half-dimensional. And so the simplest example of this is that you take a cotangent bundle of surface of high genus, and you take a cotangent bundle of surface of high genus and remove neighborhood of zero section. And then you take this form PDQ and add pullback of area form on the surface. And this pullback of area on the surface is in fact in the complement. The complement is so you take this form, and this form P sigma is in fact P star of sigma away from zero section is d of something, and then you get this lambda plus PDQ. And so this is called adding magnetic term to PDQ, such procedure. And so what happened that this near zero section, this lambda completely dominates because this goes to zero, and then because of this negative characteristic, in fact, this corresponding Liouville vector field kind of look like this near this boundary, and at infinity it's kind of standard essentially PDP vector field. So here we have a picture like this. So this manifold. And this manifold, of course, have a homotopy type of something three-dimensional, and therefore it's not a Weinstein field. So that's what this example, and such example exists, of course, in any dimension you can hook up such field. So there is a following question, which kind of was open 30 years ago and it's still open. Like, what is when Liouville filling is Weinstein. So suppose we need to have of course topology of this filling manifold must have it no more than half dimensional, but is it good enough? So what kind of recently we proved that if like you can look at this for such Liouville manifold, you can look kind of like flow z minus t going in opposite direction and take some kind of compact domain and just look of intersection of such domain, and you get some attractor of this minus Liouville vector field. And in Weinstein manifold, this attractor is some kind of Lagrangian singular skeleton. And in this case of McDuff example, you get three-dimensional hypersurface. And so suppose we know this attractor is in fact like stratified half-dimensional set, then it's Weinstein. Then you can deform it to Weinstein. But when so it's kind of something dynamic question, when can you arrange for this Liouville vector field to be half-dimensional? Okay, anyway, but so this is I was talking about.
Let's see the space of manifolds. This fixed the boundary. It will be a big open components in the high-dimensional structure. Even for standard. When it exists with manifolds, testing all manifolds, you repeat it, typically they produce high dimensional. Yeah.
So yes, so okay, so take so now so it can so there is a zero parametric question when we have this, and then you have a kind of high parametric question for us. So we can ask, we have a two Weinstein structure, so that means we are half dimensional, but then if there is symplectomorphism of such structure is in fact the same as if they are homotopic via Liouville deformation. If you have a Liouville homotopy kind of like with keep with this transversality at infinity, then it's the same as symplectomorphism and vice versa. So therefore classification of this domain up to symplectomorphism is the same as classification up to Liouville homotopy. But when the classification of the Weinstein model is equivalent to the open proof. So now I would like to kind of like this what main thing which I want to talk about. So this is all essentially old story and not much kind of development in recently about this. But there was the following kind of extremely strange development happened like about 4 or 5 years ago in the subject, and so it kind of came from dual question, but then it has some kind of ramification for this. So the kind of dual question which we want to ask, we would like to consider contact manifold with symplectic bound. Of course, this does not make any sense, because if you have a like contact manifold, then what does it mean for contact manifold to have symplectic boundary? Like in no reasonable sense, if it's a symplectic, because it's a boundary, if it's a closed manifold, it has to have a non-trivial cohomology class, then what does it mean that it has a contact, kind of any compatible contact structure? I don't know. But turns out that there is a kind of like best approximation to this is the following notion of contact convexity. So this notion also was introduced in our paper with Gromov 35 years ago, but we really just only asked questions and didn't do anything about this, just kind of like as a parallel with symplectic question. But then Emmanuel Jaroux like wrote some kind of foundational paper where he studied this notion. So let me kind of discuss this. So suppose we have now contact manifold. So we have this some manifold Y, this 2n minus 1 dimensional manifold, and we have a contact structure, which means hyperplane field, non-integrable hyperplane field. And now you have a hypersurface sigma in the contact manifold. And you would like to understand kind of what is convexity. So let's first start with a kind of similar definition. We want some vector field, and this vector field we would like to be what is called contact vector field. So the flow of this vector field Z preserves contact structure. So you would say it doesn't look like analog of Liouville field, because in Liouville case this flow rescales symplectic structure, and here I say preserves contact structure. But contact structure by its kind of definition, kind of conformal object, so it doesn't mean make any sense to talk about rescaling it. So just contact vector field. So you have a vector field which preserves the structure. So let's kind of understand a little bit better what this means. So suppose you have this contact structure given by some one form, and let's denote by say beta restriction of this. So it's given by C is equal by some alpha equal to 0, and beta is equal alpha equal to 0. And then this one form on the even dimensional manifold sigma, it cannot be contact. It has a kernel. So there is a like similar, like you have a hypersurface in symplectic manifold. This hypersurface in symplectic manifold has this Hamiltonian vector or characteristic direction where this symplectic form restricted vanishes. Exactly the same thing happened here, because like as I told you, you can think about this hypersurfaces in contact manifold as a symplectic cylinders. So this is a symplectic kind of cylinder in symplectization, and the symplectic cylinder have symplectic characteristic foliation. And the symplectic characteristic foliation invariant with respect to scaling, and therefore it projects to certain foliation on contact manifold itself. But sometimes some leaves are in fact straight vertical lines, and they project to the point. So you get a characteristic foliation of this hypersurface, but this characteristic foliation may have some singularity. So you get kind of singular characteristic relation, and the singular characteristic relation again in transverse, if I can transverse slice to this relation, then you get a contact manifold canonically. So you get again on this hypersurface in contact manifold, we have affiliation with transverse contact structure. So now what this condition that there exists transverse Liouville vector field means the following. So suppose I choose some coordinate system, let's call it coordinate t, such that t is a flow coordinate along this contact vector field. And then because I can in fact arrange the form itself, alpha, is invariant with respect to this flow, and this would imply that my contact form in the neighborhood can be written in the form beta plus fdt, where beta is this form on the slice, and f is some function, and f is just some function depends only on the coordinate on sigma. So now it's kind of very easy to check. So from contact condition, it follows that level set f equal to 0 is a regular level set of the function. It's a regular level set. And hence, what happens that the sigma by this level set, let's call it maybe C, it's divided into two halves, where my function f is positive and negative. And then if you look at this thing and contact conditions, then you can scale contact form. You can write away from C. You can write beta divided by f plus dt. And then what you check the contact condition just means that the d of beta over f is the Liouville form. And so you get the following picture. You get that my hypersurface is split into two Liouville domains, and now you can also easily check that this characteristic relation is in fact transverse to the boundary, and the boundary itself is a contact manifold. So the picture of the boundary of this convex contact domain is the following. It's a union of two Liouville domains with the same contact boundary. So like you take the same kind of some contact manifold, take Liouville filling of this one, and take maybe another Liouville filling of the same thing, and then you kind of take any contactomorphism between them and glue them together. So therefore, like notion of boundary, like what was before we were talking about contact manifold boundary symplectic, then this kind of notion in contact geometry, then we have a pair of Liouville domain with the same contact boundary, and this gives me boundary over contact manifold. So now, how kind of common is so that, and you can actually check that this is the only, so there is no kind of like in so this is kind of discrete data. So that means that suppose you have a two Liouville domain and you think about them only after symplectomorphism, kind of like it completes them to like infinite domain, and think about them after symplectomorphism or up to Liouville homotopy, which is the same thing. And you have a contactomorphism of the ideal boundary again understood up to contact isotopy. So just complete discrete data. So you have this two Liouville domain kind of abstract and contactomorphism. And then if you take any concrete realization with different Liouville form in this homotopy class, different contactomorphism, then you can always realize one of them in arbitrary small C0 neighborhood of the other. So up to some kind of C0 deformation, this is like discrete data giving me kind of essentially all information. So you can kind of now start asking the following question. So how common is this contact convexity? So what Giroux proved in his PhD dissertation actually is the following, that in dimension, suppose we have a in dimension 3. In dimension 3, this is two-dimensional surface. And on this two-dimensional surface, you have some characteristic relation. And then what he proved, that if this characteristic relation is generic, and generic just mean in kind of more small sense, generic, say, for instance, have this orbits kind of attracting or repelling, and also there is some sign. You don't want to have a, like what Giroux calls retrograde connection, kind of going from some, usually there's some positive orbit, positive, negative orbit, but anyway, there is some kind of sign condition, which also generic condition. But the main thing that any generic relation is a convex. And
So we know periodic orbits.
yeah, periodic orbit. For instance, like let's take the following example. So take torus. And if you take a torus, standard torus with quantum structure dz plus say r squared dc, kind of like, and z kind of, so this is the theta, and z is also mod 1. Take this solid torus, then characteristic relation on the boundary is just kind of some linear relation, and this is an example of something manifestly non-convex, because obviously this relation does not have any, you cannot find any curve, any divided curve like in this, which would be transverse to this relation. It would divide my surface into halves. So this is a non-convex. But then, if you perturb it, so then this is a suspension. This characteristic relation is a suspension of the diffeomorphism S1 to S1, which is rotation, and this is not convex. But if you perturb it to rotation with rational rotation number and make it generic, then would mean that kind of like periodic point all non-degenerate, then it's becoming convex. And then kind of like this dividing set would be you take this, for instance, attracting trajectory, and you just surround this attracting trajectory by some unknown. That would be the splitting. So notice you can introduce the following notion in, well, this sounds stupid, but you take a circle and you consider diffeomorphism of circle is convex if corresponding mapping cylinder is convex. And what I said, this diffeomorphism circle convex if you only have a generic diffeomorphism with rational rotation number. So I would like to ask similar question in high dimension. So let's see how general are convex surfaces in high dimension contact mechanism. So it was a kind of for almost 30 years, there was absolutely kind of nothing known about this. So after Giroux work, and until kind of something I think around 2019, when Honda-Huang wrote some paper where they claim that any hypersurface in contact manifold can be C0 approximated by convexity. Not C infinity, like in two-dimensional case, but C0. So Honda-Huang, so it's kind of any hypersurface can be C0 approximated by convex. So there was some kind of long development, the proof was not correct, but then kind of like turns out that eventually kind of it was corrected with also with help of Duchamp, Pancholi, myself, and now this is kind of theorem. So indeed, this is true, and this implies, like, let me immediately tell some kind of amazing fact. So, as I said, given contact manifold, to find like feeling of contact manifold or different feeling, it's kind of some task to do. So each time, for instance, this example of constructing requires some kind of work of people to do. And what this says, for instance, the following thing: like take any format, just whatever you want, or take S4, but take any form manifold. Then any form manifold is easy to prove, admit some germ, some of contact structure in the neighborhood of manifold cross it, just for all the things. So, and then you can make it convex. So therefore, any form manifold you can split in the union of two, and moreover, you can even this by the way I said you will, but this proof automatically gives that all halves becoming not just revealed by one step. So in particular, you have half-dimensional model. So therefore, any form manifold you can split in this way. And moreover, you don't need to work with it. You just kind of take the surface, kind of like just doing something kind of generic, and suddenly it's split. And so also, as I will explain, it implies that this splitting exists in kind of enormous quantity and all of them different. And notice that even like for the case of S4, this is an amazing result, right? So you want to split S4 as a union of two, of like find some contact tree manifold with two different feelings, such that when they glue them together, you get S4 by some contact number. And okay, you can take two balls and glue, you get S4. But you can do something else and you get it. But to get kind of like what the thing that this is actually kind of like an enormous number of such things, kind of like everywhere dense example. And like if I ask you to construct any other example, you would have to work it. You can construct. There are no examples of this type. It's like you have a contact manifold with two different feelings, and not just two different feelings, but two different feelings such that you are glued together, you get S4. And you can do it for any manifold. Okay, but let's kind of further let's continue with the story. So now this proof of Honda-Huang was kind of look like this. So what you take this manifold. So kind of like what's the strategy of the proof? So you take this hypersurface, and now you do something kind of like extremely violently kind of start to move our hypersurface to create a lot of singular points. So this you create this many singular points and try to arrange that every trajectory start and end in one of these points. You can like create a lot of singularity and arrange that there's no kind of other attractor of this flow except this thing. And this is kind of like pretty straightforward. Now what is strange that it's kind of like usually such type of technique in symplectic geometry will never work, but strangely here you can do that, and that's what we do. But what kind of we realized with Pancholi, and now we have some also joint work with Julian Chaidez about that all this in fact completely necessary. You know, you can achieve the same thing without any creation, any new singularities at all. In particular, you can do the following thing. You take a, say, well, let's take this example. You take a, like any manifold and consider any contactomorphism of this manifold and take a mapping cylinder of this contactomorphism. So you take this kind of product and you glue this with F. So you take this manifold, and now I would like to make this thing convex. In particular, split the cylinder into this way. And this can be done by, you can just compose, there is a kind of C0 small, C0 small contactomorphism such that phi composed with F is, so that the C phi composed with convex. So if you just do this definition, as I said, call diffeomorphism, contactomorphism convex if its mapping cylinder is convex, then the theorem is this convex contactomorphism RC0 dense in the group of contactomorphisms in So Chaidez before this, he kind of like worked constructed example that in some case we know that C1 is not true. So there are like, for instance, if you take say some kind of I don't know, so flow, like take a unit potential bundle of circles of high genomes and take a time one flow, and then you cannot approximate the theorem, you cannot C1 approximate this one by convex contactomorphism, for instance. But C0 you can. C0 you can. So now let's kind of a little bit understand what, let's consider the following example. Suppose M is just standard ST. So let's see what can we say about this splitting which arises for contactomorphism. So you can always think that my characteristic relation is just straight. I cut it off. So characteristic relation straight, but I glue this by my F. So let's consider this dividing set. This dividing set is some, so let's say D is, I call it already C. So let's take this, call it C hat. This is the C minus kind of like S3 cross 0. Okay? So I just cut it off, open, and this is my C hat. Sorry. So C hat projects downstairs as a notion, right? Because it's transverse to this characteristic relation. But also it divides this our manifold, and like if you consider this piece and my kind of and sigma hat, then what you see that this projection is again immersion, and because S3 is simply connected, this is diffeomorphism. So therefore, you have a kind of this dividing. This division is in fact kind of topologically extremely simple. Only so what I was trying to convince you that on one hand, I will show you that there is a fantastically many splitting, which all of them should be different. But on the other hand, all of them look pretty simple. So for instance, what it looks like. So it has to look like this. So you take some sphere, you take say Higger decomposition of the sphere, while I draw genus 1. So this is say one of my half, and this is another one. And then you have so this boundary, let's call it this boundary of this, call it say S, and then you have some map of this torus here, but it's not necessarily so it can, for instance, look like this. So you have a one piece half of Hilbert splitting, it's embedded in the other half of Hilbert splitting, and the condition that complement of the embedded one is still kind of either in the sphere isotopic to original embedding, but in the sphere. And so that means that kind of like for my dividing set, it looks like kind of like a difference between, so you just take this one solid torus minus another, for instance, the solid torus, and you identify boundary. So this is type of contraction which you can do. Okay, but now I will explain you that in fact. So while I am repeating this story that all the splitting has to be all different. Now I really explain you why. So there is a following story, and this is due to Postorovich and myself, that if you consider, for instance, R4 cross S1, then in R4 cross S1, if you, so for instance, you take a balls of radius R cross S1. And R4 cross S1, I consider the standard contact structure, some UV form here, plus DZ. And let the Z, they kind of have size 1. So then the statement which we proved that there is this kind of the following, so you're asking when this, let's call it B before R hat. When before R hat can be by contact isotopy mapped to before some R hat where R smaller than R. When can you squeeze this product to smaller one by contact isotopy? And there is a theorem kind of which says, okay, so you cannot squeeze it as long as a pi r square is greater than 1. As long as pi r square becomes less than 1, then you can squeeze. But largest radius you cannot squeeze. So in particular, when we approximate them by convex, they of course also cannot be squeezed inside the set. But then you have but convex approximation. So this characteristic filiation for the characteristic filiation for the round ball process one, it just kind of Hopf rotation. It just is kind of similar with the one-dimensional case. But now you take this Hopf rotation and C0 approximated by some convex contactomorphism, and this would give you splitting of the type I told you. And this is kind of, as I said, discrete data. So essentially, this splitting defines completely contact type of the C. So either we have all the splitting kind of, we have a very dense set of this splitting, which is all of them different, or among them there is a very dense set of embedding of the same boundary which bound not contactomorphic domain. So either of the statements sounds to me kind of incredible, because kind of like because we don't know any example. Okay, so that's what I wanted to say. Okay, so what kind of like I just would like to maybe it's too much about this journal for you, but let me just kind of say, okay, so here's the kind of few things which I would really, I think it's possible to understand, but kind of like some work to be done. So first of all, I would like really to understand, I hope we can do it in some kind of reasonable time, like in this example. So you have a Hopf rotation. You want to find convex approximation of Hopf rotation. Can we do it explicitly? if you take an identity map, it's very easy. Can you do it for anything, for any Hopf rotation by angle which is not proportional to pi? I don't know any example of this. So, like now, this kind of technique also I mentioned was useful for this problem of trying to replace Liouville structure by Weinstein. So here's the kind of like key question I would like to answer. So suppose again let's return to this problem when Weinstein domain is Stein. When the Liouville domain is Weinstein. So suppose this domain has a homotopy type of less than half-dimensional star complex. So you have a two-dimensional domain, and it has a homotopy type of less than half-dimensional copy. Then what you can prove, and this is the theorem of Oleg-Lazarev, that inside this domain you can embed, you can find kind of as a Liouville subdomain, is this one. You can find Weinstein subdomain, and moreover, this is so-called flexible Weinstein subdomain. So, in particular, type of the domain completely determined by the contact type of the domain, completely determined by contact structure on this boundary. And this is just annulus. This is just W cross 0, 1. So the whole question is reduced to question about this annular. So you have a Liouville structure on the annulus, such that Liouville will kind of enter and exit. And is it possible to make it Weinstein? We know, example, that it's not standard because it has to be some, you have to have some critical point. This old example of Chaidez, kind of like we know, for instance, example of when you cannot remove critical point. So, like you have a say ball, and you have a symplectic structure with contact boundary, but this symplectic structure, Weinstein structure, must have some other critical point. So skeleton cannot be less than half-dimensional. So the same picture happened here. So you need at least half-dimensional attractor, but kind of can you always remove it? Can you always? So I would now, if you ask me kind of like before the work of Honda-Huang, what the relation between this Weinstein and Liouville, I would say that of course there are plenty of abstraction and we just don't know how to do it. But now I kind of start to believe that in fact there is some kind of flexibility result that Liouville can always make Weinstein with topology well. I think I'll stop here.